So, according to my notes, we finished example 4 at the top of page 3 on Friday. Is that correct? Everybody in agreement with that? Right, that's where we ended. Okay. So let's take a look at example 5. We're given big F of x is equal to x plus 2 cubed minus the absolute value of x plus 2. Okay. And so big F of x is actually a composite function. It's a composite of little f, little g, right? Composite little f with little g, right? Which is equal to f of little f on g of x. Okay. What we got to do is decompose big F of x into the two smaller functions, little f of x and g of x. Okay. So last week, if I gave you f of x and g of x, you knew how to find the composite of those two functions. Now we're going to take one function and decompose it into two smaller functions. Okay. And there's really no formula for this. It's just by inspection. Okay. You have to see it with your eyes. Okay. So if you look inside big F of x here, right, you see inside big F of x, we have this algebraic expression x plus 2. And that is what we can call the inner function inside big F of x. So we can set our inner function g of x to this algebraic expression x plus 2. And there's no formula for this. You just have to recognize it. Okay. By inspection. Okay. So if we let g of x equal, right, our inner function g of x equal x plus 2, then to get the outer function f of x, we have to replace x plus 2 in big F of x with just x. Okay. And so if I replace on the right hand side up here x plus 2 with just x, that gives me the outer function little f of x. Little f of x is equal to x raised to the third power minus the absolute value of x. Okay. So you have to see the algebraic expression that you can call the inner function g of x, and then replace that algebraic expression with just x. And what you have left over is the outer function, little f of x. And so you can do a check, okay? Make sure this works. F of g of x has to equal big F of x, right? Well, little g of x is x plus 2. Right? So we replace g of x with x plus 2. And then now we got to evaluate little f at x plus 2. And to do that, you replace x in little f of x with x plus 2 on the right hand side. And when you do that, you have x plus 2 cubed minus the absolute value of x plus 2. And that equals big F of x. So our choice for an inner function and an outer function worked. Okay? Their composition equals the original function, big F of x. Okay? So this is called decomposition. Decomposing a more complex function into two simpler functions. Okay. Any questions on that? Okay. So let's take a look at example 6. We're given f of x equals square root of x minus 1 and g of x is equal to 2 over x minus 3. We'll find and simplify the composition of g with f as a function of x. So we were doing that last week. So f of x is equal to square root of x minus 1 and g of x is equal to 2 over x minus 3. So we're going to find the composition of g with f as a function of x, and by definition, that's equal to g of f of x. So you know the first step is to replace the inner function f of x with what it's equal to. And it's equal to square root of x minus 1. So this is equal to g of the square root of x minus 1. And now we evaluate function g at square root of x minus 1. So on the right hand side of g of x up here, right, we just replace x with square root of x minus 1. And we have 2 over square root of x minus 1 minus 3. So that's the composition of g with f. Okay. Now to get the composition with f with g, we have to evaluate f of g of x. So g of x is now the inner function. So we replace it with what it's equal to. It's equal to 2 over x minus 3. So we have f of 2 over x minus 3. And now to evaluate the function f at 2 over x minus 3, we just replace the x and f on the right hand side of f of x with 2 over x minus 3. So we have 2 over x minus 3 square root of 2 over x minus 3 minus 1. And I think I'm going to write down below. To simplify this under the radical, right, you're going to write 1 as the common denominator is x minus 3. So we write 1 as x minus 3 divided by x minus 3. So So we make the square root 2 over x minus 3 minus x minus 3 over x minus 3. And now we can combine the numerators because we have common denominator. So I want to emphasize when we combine the numerators, it's 2 minus x minus 3 in parentheses, right? We're not just subtracting the x, we're subtracting minus 3 as well. And so when you simplify the numerator, we have 2 minus x plus 3 over x minus 3. Right? When you distribute the minus sign, you have minus x plus 3. So 2 minus x plus 3 simplifies to 5 minus x. So this simplifies to 5 minus x over x minus 3. Okay? All right. Page 4, the back page is blank. I wish I had split the C and D. I put C and D on the back page, but I wasn't thinking that far ahead. Okay. In C, we got to find the domain of this composite function. Okay. Now, in finding the domain of a composite function, first thing you got to look at is the restrictions on the domain of the inner function. And the domain of g of x is all real numbers except for what number? Can you tell? The domain of g of x is all real numbers except for what number? 3, right? X minus 3 can equal 0, which means x can equal 3, right? Because if x equals 3, we got 3 minus 3 in the denominator, which is 0, and you can't divide by 0. Okay. So 3 is not in the domain of our composite function, okay, right off the bat. So you notice that our composite function is the square root with x under the square root. And so what's the domain of the square root function when you have x under the square root? You take this is called the radicand, and the radicand has to be greater than or equal to 0, right? Because if the radicand is equal to a negative number, you're taking the square root of a negative number, which is an imaginary number. And we're only interested in the values of x that make this quantity equal to a real number. So the radicand, so the domain of the composite function requires that the radicand 5 minus x over x minus 3 be greater than or equal to 0. Okay. If the radicand is less than 0, then we're taking the square root of a negative number, which is an imaginary, not a real number. We're only interested in the real values for our function. Well, this is a rational inequality. We know how to solve those. We did this in section 1.1. This is exam 1 material. Okay. Math is cumulative, right? What we were doing in the first week of January, we're still doing in February. Okay? Yeah. So this is a rational inequality. Okay, so this is where you might have to flip over to the back page, okay, the blank page, to do this rational inequality. And so, the steps in solving a rational inequality, okay, that's why I wish I had put C at the top of page 4 and D in the middle, but I wasn't thinking that far ahead. Step 1 in solving a rational inequality is make sure you got 0 on one side of the inequality, which we do. Step 2, you set the numerator and the denominator both equal to 0, and you solve for x. You get x equals 5 and x equals 3. And then you plot those numbers on the real number line for the variable x. So we got 3 and 5. And we already know 3 is not in the domain. So we put an open circle on it. We would also know 3 is not in the domain from this rational inequality. This 3 would make the denominator equal to 0. 5 is in the domain. Because when you put in 5 in for x here, you get 5 minus 5 over 5 minus 3, which is 0 over 2, which is equal to 0. And the inequality symbol is greater than or equal to 0. So 5 makes the left-hand side equal to 0. So it's in the domain. And now you got to do the test point method for those 3 intervals. Okay, remember that? Okay. And when we do, how many of you want me to do the test point method? How many of you want me to just give you the result? Just give the result, right? You should be able to do the test point method on your own, okay? So, when I did the test point method, using numbers less than 3 made the left-hand side over here less than 0. So they didn't work. When I used numbers between 3 and 5, right, greater than 3 and less than 5, they made the left-hand side over here greater than 0. So those numbers work. And when I use real numbers greater than 5 in for x over here, the left-hand side was less than 0. So those numbers didn't work. Okay. And so the only numbers that make the left-hand side greater than or equal to 0 are the real numbers greater than 3 and less than or equal to 5. And that is the domain of our composite function. Okay. So the domain in interval notation left parenthesis 3, 5 bracket. Okay. So I'll just write on the board here, right? This is the result of doing the test point method. Okay. Section 1.1. Alright. And actually you got problems like this on the exam review, don't you? If you read the exam review, you know you got, right? 2.1 was finding the domain of functions, right? And so you got problems, problems like this on the exam review where you have to find the domain of a square root function. And you got to take what's under the radical, set it greater than or equal to 0, and do the solve the rational inequality. All right. And D, you gotta find the domain of this function right here. Okay. Well, f of x is the inner function. So we gotta look at the restrictions on f of x. And so here's f of x, right? This is equal to square root of x minus 1. And so its radicand has to be greater than or equal to 0. Now, fortunately, that's a linear inequality, right? Not a rational inequality. So when you add 1 to both sides, right, x has to be greater than or equal to 1. So that's the first restriction on the domain of this composite function, right? X has to be greater than or equal to 1. Okay. So let's draw that preliminary graph. Right, here's minus 1, 0, 1, 2, 3, 4, so forth, right? So here's 1, with everything shaded to the right. Okay. Now there are going to be other restrictions, but this is where we're at right now with x greater than or equal to 1 based on after that. Okay. All right. So here's the composite function, right? The second restriction, right, on this domain of this composite function is the denominator can't equal 0, right? So we have the square root of x minus 1 minus 3 can't equal 0. Okay. That's the second restriction on the composite function, right? The first one is x minus, right, under the square root, x minus 1 has to be greater than or equal to 0. The second restriction is this denominator can't equal 0. Okay. So we add 3 to both sides, and we get the square root of x minus 1 can't equal 3. And then we square both sides. We get x minus 1 can't equal 9. And then we add 1 to both sides, and we get x can't equal 10. Okay? If x equals 10, then we have 10 minus 1 under the square root, which is equal to 9. Square root of 9 is 3, and 3 minus 3 is 0. So 10 makes this denominator equal to 0. So 10's not in the domain. So we got to put an open circle on the number 10. So here's 4, 5, 6, 7, 8, 9, 10, 11, 12, so forth, right? So here's 10, open circle on 10, and then everything is shaded up to 10 and after 10. And so that's the graph of the domain of our composite function. X has to be greater than or equal to 1, not equal to 10. So how we write that in interval notation? Left bracket, 1, comma 10, right parentheses, union, left parentheses, 10 to infinity. That is the domain of this composite function right here. Those are the numbers you can put in for x here on the right hand side in the function. Any questions on it? So you now have everything you need to successfully complete the WebAssign homework.